Tokio is the most downloaded async Rust crate of all time. It powers thousands of production services at top tech companies. The engineering that went into creating Tokio is quite fascinating and reveals a lot about why Rust is a great systems language. But most developers have no idea how Tokio actually works under the hood. So that's what we'll cover in this video. So grab a notepad, get your popcorn ready, and let's dive right in. Exciting news! This video is part of the official launch series for the Rust Live Accelerator, opening this June. More on that later. Async Rust code that uses Tokio starts with this single line, the Tokio main attribute. This is a macro that turns the main function into this. Two things to notice. The first chunk builds the Tokio async runtime that actually runs async code. Then block on is called. Block on takes the original code in the main function, wraps it in an async block, and hands that async block off to the Tokio runtime for execution. So the Tokio main macro basically does two things: builds an async runtime, then calls block on to run your code on the runtime. Now that seems pretty straightforward, but to be able to appreciate the genius behind the Tokio async runtime, we need to pull it apart and understand how it works under the hood. The Tokio runtime is made up of 7 components that we'll dig into in this video. Let's cover them one by one. Keep in mind, these diagrams are simplified and optimized for conceptual understanding. The first component we'll talk about is the task. A task is Tokio's unit of work. The runtime tracks each one from creation all the way to completion. Tasks are cheap, about 64 bytes each, versus roughly a megabyte or more for an OS thread. That's 15,000 times smaller, which is why a single process can hold millions of tasks at once. But how do tasks actually get scheduled and executed? That's why we have the scheduler and executor. The scheduler is the task dispatcher. It decides which task runs on which thread and schedules it. The executor executes tasks scheduled by the scheduler. The amazing thing about Tokio's scheduler is this: when a thread runs out of tasks to work on, the scheduler doesn't allow it to stay idle. Instead, Tokio's scheduler does what's called work stealing, which allows it to steal work from busy threads and give it to threads that are sitting idle. This keeps every CPU core productive. This unique work-stealing design landed in November 2019 and made Tokio 10 times faster than any previous version. Now, to schedule the tasks, the scheduler has access to 2 types of queues: local queues and a global queue. The first type is going to be the local queues. The Tokio runtime creates a pool of worker threads, and every worker thread has its own local queue. Here we have 4 threads, so there are 4 local queues. Each one is private to its worker. No other thread reads from it. Tokio local queues use an interesting data structure called a ring buffer. It's around 256 slots, which is small on purpose so it fits in CPU cache. When a worker thread pulls its next task, the queue head is almost always already hot in L1 cache for very fast access. And the great thing is, there are no locks necessary on the hot path when picking up a new task. A worker thread pulls from its own local queue without requiring a mutex. That lock-free work-stealing design is a big part of how Tokio achieves high performance. The second type of Tokio task queue is the global queue. One single queue shared globally across every worker thread. The global queue's main job is to absorb overflow when a worker's local queue fills up. Tokio uses a hybrid queue model: local queues for speed and a global queue for backup. Worker threads check their local queues first, fall back to global, and only steal from peers when both their local and the global queue are empty. Now, taking a step back, the whole point of having an async codebase is to handle async operations efficiently. Operations such as network requests or reading from the file system. In the case of Tokio, when a task needs to wait for some async IO operation to complete, it needs to come off the worker thread and talk to the Reactor component. The Reactor, sometimes called the IO driver, is the bridge between your async tasks and the operating system. When we need to wait for IO operations, we must notify the Reactor. The Reactor takes what's called a waker, registers interest with the OS, and parks the task, allowing the worker thread to run other tasks. Then, when the IO operation is ready, the OS signals back up to the Reactor, which wakes the task and makes it runnable again. Under the hood, the Reactor sits on top of Mio, Carl Lurch's crate, which actually predates Tokio itself. Mio is the thinnest safe Rust layer you can put over the various OS event APIs for Mac, Linux, and Windows, all under one unified API in Rust. Now that we've talked through every major component in Tokio, let's put everything together and visualize the initial code snippet from the start of the video. Our async main creates a task and wraps the code inside of it, and pushes it onto the queue. Let's assume it moves onto a local queue because we don't have any backed up work to spill into the global queue. The worker thread for that local queue picks the task up. The executor drives the code forward, but eventually we need to wait for the I/O piece of the code to be ready. In this case, a call to fetch user, which we can assume is a database request. That's when the reactor steps in. It takes the waker, registers interest with the OS, and parks the task. The important thing is, the worker thread is now free. It can pick up other work instead of blocking on this single request. On the OS side, it watches and waits for the database request to complete. When the response is ready, the OS signals back up the chain. The reactor receives that wake, marks the task runnable, and the scheduler enqueues it to any open worker thread. Let's assume thread 4 is open this time around. The executor again runs the task, but now on thread 4. That's one full lifecycle of a single async task inside the Tokio runtime. And the beauty of Tokio is that it can easily scale to run a massive amount of tasks concurrently. To see this in practice, let's look at a more realistic example. Imagine that we want to implement a web server in Rust. Each request creates a new async task, which means Tokio needs to run thousands of these tasks concurrently. Fortunately, Tokio is built for exactly this kind of workload. In Tokio's own scheduler benchmarks, a HTTP server powered by Tokio handled over 150,000 requests per second on a single thread. That kind of throughput is only possible because of the lightweight tasks and scheduler design we just walked through. Now you know how Tokio works, but you know what's better than knowing how Tokio works? Being able to engineer libraries like Tokio. That's exactly the type of things our students are doing in our Rust Live Accelerator mentorship program. We're opening 30 spots for the next cohort this June, which is only a few weeks away. So click the link below to join the waitlist and reserve your spot. If you've built Rust programs using AI, but you never really felt 100% confident knowing what the code actually does, this program is for you. Inside, you'll be mentored by professional Rust developers who will give you code reviews, help you with architecture, and get you to the point where you can build production-grade Rust software with confidence. On top of that, we have a team of recruiters and career coaches who will help you turn those skills into high-paying Rust roles. We've helped hundreds of developers and we want to do the same for you. So click the link below to join the waitlist. You'll be the first to know when applications open, and you'll also get our 3-step Rust developer roadmap as a small gift. So tap the link, join the waitlist, and I'll see you inside.